Thank you, everyone. Uh, I am very nervous, so I'm going to take this here to know. Hello, everyone. As Santiago says, my name is Estiven Rodríguez. I am master student, and this presentation is part of my research, which is advised by the Professor Juan Fernando Salazar and Juan Camilo Villegas. So let's start. I want to start talking about the meaning of the scaling laws that we make reference here. When we talk about scaling law, we are making reference to certain power laws like this that basically represent how is the spatial behavior of certain processes or with increase of the observation scale. So when we talk of hydrologic scaling, we are talking about how is the spatial behavior of a stream flow when or with increase in spatial in multiple scale. When how how is the behavior of the stream flow with spatial scale? In this case, the scale parameter is the drainage area, and alpha and beta are the scaling properties that govern these power laws, these scaling laws. So look at the picture. This, I don't know if you can say, but along this drainage, there are a lot of stream flow gauges, which each one gauge have a drainage area associated. So when we take in consideration all these gauges into these power laws, we have physical information of how is the spatial behavior of stream flow in multiple scale, and also how is the capacity of the basins to regulate its stream flow across a scale. So we translate this power law to the log space and obtain this linear equation. To obtain the parameters scale alpha and beta that are the properties that govern these power laws, these scaling laws, we make use of standard least square methods. I want to note that these are ordinary moments of the statistical probability functions. So we can obtain all the information, all the statistical information of the stream flow, just taking into account the drainage area of the basin and this two parameter basin scale. Okay. So the first important question that we investigate is about the stationarity hypothesis that is used in traditional methods of stream flow estimation. Traditionally, this is supposed stationary. It means that the probability distribution function are not changing with time. But we consider that due to climate change and environmental global change, the superficial hydrologic dynamics are affected. So these power laws, or these linear laws in this case, are changing with times. For that, we make use not of this equation, but also this, where we consider the annual stream flow, both stream and mean stream flow, and evaluate this equation through this time period, beginning in 1974 and finally in 2030. A second important question that we make in this research is about what represents these scaling laws, what is the meaning of these scaling laws. So in terms of stream flow regulation, we hope that the spatial growing of low flows be something like this. It means we hope that low flows, we hope that the growing of low flows be more gradual while with increase in spatial scale in drainage area. And two, we expect that the floods, that the spatial growing of floods be something like this. These two cases are an ideal case, what represent that the severity of the stream are decreased, are lower, while greater be the area. It means low flows are greater when with increase in area, and floods are lower, are less greater when with increase in area. So these power laws can be represented in the log space by something like this. When I say this is an ideal case when the slope, note that the scaling exponent, that is the property that determines how is the concavity of this power function, the scaling exponent corresponds to the slope of this linear function. So in this case, we have that for low flows, the slope is greater than the slope of flood. In this way, what we infer of these graphs is that the spatial or the severity of the stream flow, it means the stream flow are less streams with respect to the main stream flow when with increase in drainage area. Well, all this analysis was made in 7 basins, 7 large-scale basins located in tropical South America. Here, the Magdalena Basin and the Wall Amazon Basin. In the Wall Amazon Basin, we have 6 principal basins: Negro, Solimoes, Madeira, Tapajós, and Chingú. So we make the analysis of scaling in each one of these, and well, the information was obtained from Sohiban projects and from Hidroclimatología here for the Magdalena Basin. The stream flow gauges that are these points are variable with time. It's mean years after years, we can take different numbers of gauges to make the analysis of scaling. This is a consequence of that not all these gauges have the same stream flow records in the studied period. So this is some of the results. These are linear regression obtained through the standard methods. And we can say here that there are some basins in which the spatial behavior of stream flow is the spatial behavior of the stream flow is reducing with a through drainage area. But there are some basins in which the stream flow are increasing with respect to main flows, while with increasing in a spatial scale. Results like this were obtained for all the 40 years, for all the periods. So we obtained a lot of graphs like this, and when we graphs all that results, we obtain the temporal evolution of the scaling properties. In this graph, I am showing the scaling exponent, just the scaling exponent, not the coefficient alpha, just beta. And I am showing that the temporal evolution of the scaling exponent for low flows, the temporal evolution of the scaling exponent for fluids, and for main flows. The most important conclusion that we can take of these results is that we found a statistical significant trend in the most of the temporal evolution in each of these basins. So the red lines are significant trends, and there are some temporal evolution of the scaling that have no changing with time, but other, yes, are changing. So it is important to take in consideration, evaluate this stationarity hypothesis, because what we are showing here is that the stream flow record are changing with time. Okay. The second question that we evaluate was about how is the behavior of this stream flow of this scaling exponent. These results are box plots by the scaling exponent. In the left, we have for the scaling exponent box plot for low flows, and in the center are the scaling exponent box plot for main flow, and this is for fluids in each of the studied basin. We have some relevant patterns. There are some basins, Negro, Solimoes, Chingu, and Amazon, when the more than the 80% of the scaling exponent for low flows, it means these are greater than 1 and greater to the scaling exponent for the fluids. This means that this basin, Negro, Solimoe, Chingu, and Amazon, have this behavior where the low flows behavior growing is like this, and for fluids, the growing is something like this. It means that the severity of the stream flow are reducing with the spatial scale. So we interpret this like these basins are very regulated basins, have the capacity to regulate the severity of its stream across a scale. The opposed case is for the Tapajós Basin here, where there are not significant difference between the scaling exponent of low flows and floods. And in turns, there are the scaling exponent are very similar to one value. This means that the stream flow growing in this basin is something like this. Is linear. The basin have no capacity to control, to regulate its stream flow. And intermediate, we have the case of the Madeira and the Magdalena Basin, in which more than 75% of the scaling exponent for low flows are greater than the scaling exponent for floods. This is this case and this another case. This also is an characteristic of regulation, but is less regulation than in another basin, because here the low flow scaling exponent is very similar to one. So the spatial behavior of the low flow growing in Madeira and Magdalena Basin is just a linear, have a linear behavior. Well, to conclude, we think that now, again, it's very important to evaluate the stationarity hypothesis when we consider the ordinary moments of the probability distribution functions. Because due to climate change and environmental change, the superficial dynamics of this basin are changing. And this result contribute to the understanding of the dynamics of hydrological processes that give rise to the production of flows in watersheds. Okay, thank you. Thank you.
First of all, thank you, Estiven. What a great presentation. I have a question. You can tell to us about what kind of elements can influence the different scaling factors in the different basins?
Well, that is a good question. Basically, the hydrological response of each of these basins is different, because these basins are sometidos. How do you say sometido? Please. Someted. This basin, the hydrological response of this basin are submitted to different climate condition, different anthropic condition. For example, we have in this basin, the Solimoes basin, which have the most ideal behavior in terms of regulation, have the less anthropic interventions. And the Tapajos Basin is very, very deforested. So the deforestation alter the capacity of the basin to regulate its stream flow. For example, altering the capacity to retain water in a drought, in drought. Deforestation, climate condition. This basin, the climate condition of this basin are very different to the climate condition of this other basin. So there are a lot of factors that can influence these results, but we are not considering it because it's very complex. Thanks.
Thank you.